Hello, my name is Todd Byers and I'm from Tarleton State University. I will be doing my legacy project over problem 3.17 out of the book. Problem 3.17 part A asks you to find the potential inside and outside of a spherical shell given that the potential is a constant V naught over the surface of the sphere. I'll be using these three equations here. This equation is the general solution for finding the potential in spherical coordinates. This solution is from example 3.6 where they found the potential inside of the sphere. This is from example 3.7 which asks you to find the potential outside of the sphere. Okay, we'll begin with the inside of the sphere where we'll throw out the B sub L component right off. And knowing that V naught is constant for the sphere, we can pull it out and get this equation here. Now I'm going to do something with this Legendre polynomial right here. Using this table, we can see that for P naught of x, you get a 1. So what I'm going to do is I'm going to just take and insert right in here a P naught cosine theta. Since all I'm doing is multiplying by 1. I'm going to use this integral to find my solutions, of which there's only going to be two. There's going to be one for when L equals 0, and then there's going to be for all the rest when it doesn't equal 0. And for all the other ones, when you don't have it equaling 0, you're going to wind up with the 0 for a solution. But when L equals 0, you're only going to wind up with a sine theta d theta, because these will both go back to 1. Integrating that, just bring it down over here. When you integrate it, you're going to get a negative cosine pi plus a cosine 0, and that's going to equal 2. So that's 1. That's negative 1 inside of negative 1. And this one here is just going to go to 1. You're going to use that, plug that back into here. There it is right there. And when you do, all of these are going to be... Okay, it's working now. And when you do, you're going to have all of these going to 0. That's going to be 0. That's going to have 0. Which means that this term's going to go away. This term's going to cancel with this term. And that R sub L right there is going to be a 1. So you wind up with just a V naught. And then you're going to take this and plug this in for that A naught right there. When you do, you're going to have V naught. R is going to be a 1. And then you have P naught cosine, which is also 1. Giving you a result of just V naught. And this matches earlier results found in the book in chapter 2 of the book. Okay, now I'm going to go on to the outside of the sphere. And it's pretty much going to be the same sing and dance. Only instead of the A, you're going to use the R, or the B. You're going to use the same method. You're going to pull the V naught out, shove it over here, and then go through, add in your P naught cosine theta, which of course equals 1. You're going to do that, bring it down into here, get your solution. That's going to equal 2, just like it did in the previous one. So then you're going to wind up with this. Setting B sub L to 0, you're going to have a 0 here, plus 1, a 2. There's your V naught, your R to the 1, and then you got your 2. 2's cancel. You got your 1 there, that goes down, so you just have V naught R. Oh, that's off the screen. V naught R. That's what, and that's your solution for your B is a 0. Then you're going to plug it back in right here. When you do, you're going to have V equal to V naught R over R to the 1 times your P naught cosine theta. That's going to be 1. So for the outside of the sphere, you're going to wind up having a V equal V naught R over R. And this checks out as well, because once you get past it, and this checks out as well, because when you're outside of the sphere, you get a 1 over R term, and when you're inside, you just get the V naught. Okay, now I'm going to start part B of the problem, which is pretty much the same sing and dance, only this time the spherical shell has a uniform surface charge of sigma naught. And instead of using the results that we did earlier, we're going to go ahead and break up our general solution into 2 separate equations, like they did in 3.9. And this allows us to take and set them equal to each other, cancel some stuff out here, and then we move this over to this side, and you wind up with this equation here. This will allow us to just work with A sub L instead of having to fool with B as well. And this is our A sub L equation. They went through the steps to find it in the example 3.9, and I pulled it from there. But because this is constant, you can take and pull it out, pull the density out as well, just like we did in the other one. When you do that, if you notice, you've got the same equation there. So we're just going to do the same thing. We're going to plug the P naught in, use this to get our 2. L equals 0, L doesn't equal 0. Solve it for L sub 0 and get a 2. Then we're going to take and move that down, bring it down here, back into the solution. Go through, get rid of all your L's, so that you have a sub 0 equal to 1 over, that cancels, so you just have R naught, or R over epsilon naught times sigma naught. And then you wind up plugging that back into here to get your BO, R sigma naught over epsilon naught times R. It's the 1, so you wind up with an R squared sigma naught over epsilon naught. Now we're ready to solve for the inside of the sphere, which is pretty straightforward now that we've already got all the steps out of the way. You just have to take the A naught that we have from before, take that to 1, and then you get an R sigma naught over epsilon naught, and this goes to 1. So this is your V for inside the sphere there. It's a lot more straightforward, pretty simple. I tend to prefer it over the other method. For the outside of the sphere, it's the same sing and dance, only you go back up here and you grab your B now, right there. bring it down to here. I think, yeah, we'll just move this down here like this. Plug that in. Okay. That goes to 1. Got a little R down on the bottom. And this is your solution for V outside, which all matches pretty good. You still got your proportionality for the V is proportional to 1 over R. And then this is pretty much constant there. And that's all there is. Thank you for your time and have a good day.